Hello everyone, my name is Rohit and I'm here to give the presentation on the topic particle in a box, infinite potential well, and particle in a box. In quantum mechanics, the particle in a box model, it is also known as the infinite potential well or the infinite square well. It describes a particle free to move in a small space surrounded by impenetrable barriers. The model is mainly used as a hypothetical example to illustrate the differences between classical and quantum systems. And in classical systems, for example, the particle trapped inside a large box can move at any speed within the box, and it is more likely to be found at one position than another. However, when the well becomes very narrow on the scale of a few nanometers, quantum uh, effects become important. The particle may only occupy certain positive energy levels. Likewise, it can never have zero energy, meaning that the particle can never sit still. Additionally, it is more likely to be found at certain positions than at others, depending on its energy level. The particle may never be detected at certain positions known as spatial modes. Next, the particle in a model box is one of the very few problems in quantum mechanics which can be solved analytically without approximations. Due to its simplicity, the model allows insight into quantum effects without the need for complicated mathematics. It serves as a simple illustration of how energy quantizations, that is, energy levels, which are found in more complicated quantum systems such as atoms and molecules, come about. It is one of the first quantum mechanics problems taught in undergraduate physics courses, and it is commonly used as an approximation for more complicated quantum systems. And next, one dimensional solution. The simplest form of the particle in a box model considers a one dimensional system. Hence, the particle may only move backwards and forwards along a straight line with impenetrable barriers at either end. The walls of one dimensional box may be seen as regions of space with an infinitely large potential energy. Conversely, the interior of the box has a constant, that is a zero potential energy. This means that no forces act upon the particle inside the box and it can move freely in that region. However, infinitely large forces repel the particle if it touches the walls of the box, preventing it from escaping. Next, the potential energy in this model is given as V of x equals to 0, xc minus L by 2 less than xc plus L by 2, and infinity otherwise, where L is the length of the box, xc is the location of the center of the box, and x is the position of the particle within the box. Simple cases include the centered box x equals to 0 and the shifted box x equals to L by 2. Next, positive wave function. In quantum mechanics, the wavelength gives the most fundamental description of the behavior of a particle. The measurable properties of the particle such as its position, momentum, and energy, may all be derived from the wave function. The wave function psi of x comma t can be found by solving the Schrodinger equation for the system uh, I h cut dou by dou t psi of x comma t equals to minus h cut squared by 2m into dou square by dou x square psi of x comma t plus v of x into psi of x comma t, where h cut is reduced Planck constant and m is the mass of the particle, and I is the imaginary unit, and t is the time. Inside the box, no forces act upon the particle, which means that the part of the wave function inside the box oscillates through space and time with the same form as a free particle. Psi of x comma t equals to a sin of kx plus b cos of kx into e power minus omega t, where a and b are arbitrary constants. Arbitrary complex numbers. The frequency of the oscillations through space and time is given by the wave number k and the angular frequency omega respectively. These are both related to the total energy of the particle expression. E equals to h cut omega equals to h cut square k square by 2m, which is known as the dispersion relation for a free particle. Here one must notice that now, since the particle is not entirely free but under the influence of a potential, the potential we described above, the energy of the particle given above is not the same thing as p square by 2m, where p is the momentum of the particle, and thus the wave number k above actually describes the energy states of the particle, not the momentum states. That is, it turns out that the momentum of the particle is not given by p equals to h cut into p into k. In this sense, it is quite dangerous to call the number k a wave number, since it is not related to momentum like wave number usually is. The rationale for calling k the wave number is that it enumerates the number of crests that the wave function has inside the box, and in this sense it is a wave number. This discrepancy can be seen more clearly below. When we find out that the energy spectrum of the particle is discrete, only discrete values of the energy are unknown, but the momentum spectrum is continuous. Momentum can vary continuously, and in particularly the relation E equals to p square by 2m for the energy and momentum of the particle does not hold. And as said above, the reason this relation between energy and momentum does not hold is that the particle is not free, but there is a potential but there is a potential V in the system, and the energy of the particle is E equals to T plus V, where T is the kinetic and V is the potential energy. The size or amplitude of the wave function at a given position is related to the probability of finding a particle. Thereby, P of x comma t equals to modulus psi of x comma t whole square. The wave function must therefore vanish everywhere beyond the edges of the box. Also, the amplitude of the wave function may not jump abruptly from one point to the next. These two conditions are only satisfied by wave functions within the form psi n x comma t equals to a sine of kn into x minus xc plus L by 2 into e power minus I omega nt, where kn equals to n pi by L and en is equals to h cut omega n, which is equals to n square pi square h cut square by 2m L square, where n is a positive integer, that is a 1 2 3 4 and so on. And next, here this diagram represents that the initial wave functions for the first four states in a one-dimensional particle in a box. For a shifted box xc equals to L by 2, the solution is a particularly simple. The simplest solutions kn equals to 0 or a equals to 0 both yield the trivial wave function psi of x equals to 0, which describes a particle that does not exist everywhere in the system. Negative values of n are neglected since they give wave functions identical to the positive n solutions except for a physically unimportant sign change. Here one sees that only a discrete set of energy values and wave numbers k are allowed for the particle. Usually in quantum mechanics, it is also demanded that the wave function itself continues. And here is demand. Here is here this demand could lead to the only solution being the constant zero function, which is not what we desire. So we give up this demand, as this type with the infinite potential can be regarded as a non-physical abstract limiting case. We can treat it as much and bend the rules. Note that giving up this demand means that the wave function is not a differentiable function at the boundary of the box, and thus it can be said that the wave function does not solve the Schrödinger equation at the boundary points x equals to 0 and x equals to L, but does solve it everywhere else. Finally, the unknown constant a may be found by normalizing the wave function so that the probability density of finding the particle in the system is 1. Mathematically, integral 0 to L modulus pi of x whole square dx equals to 1. The particle must be somewhere. It follows that modulus a equals to under root 2 by L. Thus, a may be any complex number with absolute value under root 2 by L. This different values of a yield the same physical state, so a equals to under root 2 by L can be selected to simplify. It is expected that the eigenvalues, that is the energy En of the box, should be the same regardless to its position in space, but psi n x comma t changes. Notice that xc minus L by 2 represents a phase shift in the wave function. This phase shift has no effect when solving the Schrödinger equation, and therefore does not affect the eigenvalue. If we set the origin of coordinates to the center of the box, we can rewrite the spatial part of the wave function succinctly as the formula phi of psi n of x, which is equals to under root 2 by L sine of knx for n is even, under root of 2 by L cos of knx for n is odd. Next topic, momentum wave function. The momentum wave function is proportional to Fourier transform of the position wave function with the k equals to p by h cut. Note that the parameter k describing the momentum wave function below is exactly the special kn above linked to the energy eigenvalues. The momentum wave function is given by pi n p comma t, which is equals to 1 by under root of 2 pi h cut and integral minus infinity to infinity psi n of x comma t e power minus I kx dx, which is equals to under root of L by L by pi h cut into n pi by n pi plus kl into sin c of half into n pi minus kl into e power minus I k xc into e power I into n minus 1 pi by 2 into e power minus I omega n t. And thank you.